Okay. Um, so this lecture, now we understood what binning is all about. What do you mean by equal width binning, equal frequency binning, or quantile binning? And we came to know how to manage skewed data also. Okay. So different transformations. We came to know that you can apply. There are some limitations of log transformations. There are some limitations of other transformations. Okay. So you can apply U Johnson transformation as well, which can work for both positive and negative data values. Okay, and can manage the skewed data. Fine. So that's all about noisy data section using binning. Towards the end of the lecture, also today's lecture, we will learn about wavelets. Okay, so how discrete wavelet transform can also help you to reduce noisy data. Okay, or how we can use DWT or discrete wavelet transform to handle noisy data. Okay, so there is an algorithm known as pyramid algorithm that also we will see based on Haar wavelets. Okay, what is a wavelet and all we'll see today. That's towards the end of the lecture today. But anyway, so this will start with feature scaling. Sometimes you have to standardize your data. Okay, standardize your data. So it's an essential pre-processing step, like in data pre-processing. It's one of the essential steps. So, and you will see this in many machine learning algorithms, of course. Mainly, you will see this normalization strategy in many machine learning algorithms. So it ensures that your each features contribute equally to the model, and also it involves itself in gradient descent algorithm. You will see in next semester how it is defined. So for every value variable x, you have this normalization. Okay. So what you do, you compute the maximum and minimum element of the data set, and you normalize it according to this way. You subtract it from min and then divide by the difference between max and min. Okay. So when like this, like after you have seen this, can I ask you, when x becomes x max, what is the value of x prime? Can you just put, instead of this value x, can you just put x max and see? 1. So x prime is 1. If you put x equals to, say, x min, what is x prime? 0, right? So you can see when you put x min, thus the normalized value returns 0. When you put x max, the maximum variable, it returns the normalized value to be 1, right? So therefore, you can say that whatever values x will be in your data set doesn't matter. But when you apply this normalization strategy, all of your data variables will be transformed into the region of 0, 1. All values will lie in between 0, 1. So that's the normalization we are doing here. Okay. So you can think of this as a convex combination, actually. You can think this as a convex combination. Convex combination you will learn more in your optimization course. Those will be taking, but it's more like you have one minimum point, you have one maximum point. What you want is all points in between those two points. How you can do that? You can apply a convex combination. That's a very nice strategy. You can apply linear convex combination to take any points in between these 2 points. Okay, so it's a kind of that. So you can see the method rescales the data into a fixed range that is in between 0 and 1. Okay, so this I already told you, the smallest value becomes 0. We saw when you take x equals to x min, x prime becomes 0. When you take x equals to x max, x prime becomes 1. Okay. So all other values, the largest becomes 1. All other values are proportionally scaled. Proportionally scaled. Okay. Using this normalization. Fine. So this is known as the min-max scaling or normalization. So based on that, we can just do a small example just to give you an idea. This I have taken from a book, Kendall book available in library also. So let us see this example over here. So suppose, take this as question 1. It's question 2, okay. So suppose this is the question. Suppose that the minimum and maximum values of attribute income, like income is an attribute in one of your data sets, and this is $12,000, $98,000. $12,000 and another attribute is $98,000. So what we would like to do is to map the income, this income in the range of 0, 1. Okay. So how we can do that? Okay. So you can do that by min-max normalization. Okay. How you can do that? Like you can see where this value maps to, right? So for that, what you have to do, this is your normalization. X prime equals to x minus x min divided by x max minus x min, right? So here x equals to the first value of x is, say, suppose this 73,600, right? So what you have to do, what is the minimum? Minimum and maximum value is already given to you. So x prime equals to what you have to do? 73 times 73,600 minus the min. What is the min? Okay. Divided by max is, yes, minus 12, right? So you can see same value you are getting over here. Okay. So you can see this value turned out to be 0.716. 0.716. Okay, so you can see any value, and 73,600 lies in between. This value lies in between your minimum and the maximum, that is 98,000. Isn't it? It lies in between the minimum and maximum. Okay, and you can see any value in between the two always gets mapped to a proportional quantity, right? Understood? So this value minimum will map to 1. Sorry, minimum will map to 0, maximum will map to 1. So 73,600 lies in between these two values. So therefore it has to be proportional to, like, it should lie proportionally in between 0 and 1. So therefore you got the answer 0.716, and hence you can think that it is correct. If your answer was 2.716, if your answer was 2.716, straightforwardly you can say some wrong mistake is made, because your answer should always lie in between 0 and 1. I hope that's so. In this way you can check your correctness of your working, okay, steps. Another same question, like here, yeah, with the z-score normalization that we will look into now. After that we'll come to that example. So yeah. So last class also we have seen this quantity already. So z-score normalization. What you do, you subtract for, so each value of your data set will have its corresponding z-score. Each value of your data set will have its corresponding z-score, right? So each value of your data set represented by x, that you subtract by the mean and then divide by the standard deviation, right? So you can see this is how we standardize using z-score normalization. Okay, so you normalize it by, so you see how far it lies from the mean, and also you standardize by dividing it by the standard deviation sigma. So you can see it centers around 0. Of course, it centers around 0, and the standard deviation of 1. Yeah. So let us suppose x prime is a positive quantity. Suppose you got x prime to a positive quantity. What is the meaning of this? X prime is positive means, see, mean can be positive or negative, right? Mean can be positive or negative, but standard deviation should always be, yeah, yeah. So this is another one for you. Like, is standard deviation always positive? Is variance always positive? That you have to check out. That you have to check. Hmm? Hmm. Hmm. Okay. Okay. Anyway, these are the catchy questions which many of you might just confuse over any day, and this is what you guys have to be very much comfortable about. Okay. So yeah. Anyway, so x prime. Suppose x prime is greater than 0. That means x is greater than mu. So you can see, so x is greater than mu. So you can see the values are above the mean. Positive values are above the mean. Whereas if you have negative values, what does it mean? X minus mu has to be less than 0. That means x is less than mu. That means the values are less than the mean. Is it okay? So I hope you understand this logic over here. Okay. I hope you understand the logic over here. The positive values means this quantity is getting positive. How this can be positive? The numerator has to be positive. X greater than mu. It can only be possible when x is greater than mu. So therefore I am telling it lies above the mean. It lies above the mean. It's okay. Similarly, there are different other scaling behaviors, like something known as robust scaling. robust scaling, where where you subtract by the median, not the mean, and you standardize it with not the sigma, but with interquartile range. So it's same. You can compare both of them. It's just the same, but the mu, you are using mean here, but rather you are using median here. So in the robust, in the sense, why it is known as robust, because median is a good central tendency measure for median is a good central tendency measure over mean for 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 skewed data, left skewed or right skewed, any skewed you take. We saw that day that median is a good quantity because median doesn't change much, whereas mean gets pulled away with the skewness, right? If it is right skewed, mean will go that side. If it is left skewed, mean will go that side. Only in the normal distribution, all three quantities are same, right? Hope that is okay, right? So you can see you are subtracting by the median but not the mean, and you're standardizing it by the interquartile range and not the sigma. So therefore it is known as robust scaling technique. Okay. So, but you can see the similarity between these two. You can see the similarity between these two. Just the quantity you subtract with. Okay. So you can see previously it was centering around the zero data, but here it is centering around the median instead of the mean. Okay, because you have median over here. Okay, fine. Fine. So I hope this many of you might have done already. This many of you might have done already. Like percentage. Percentage. How we see you have scored 76 marks out of 100. We call it 76 marks out of 100. But if you want to see as a standardization process, you call it as in percentage. So you divide 76 by 100, right? The max. What is the max in your exam set? 100. And you scored 76 out of it. So 76 by 100. So, but maybe in some of your quantities can be negative or positive. Depending on that, you can take the modulus also. Okay, modulus. Means modulus of -3 is 3. Modulus of 3 is also 3. Okay. I hope that is okay. Just divide by the max. I mean, just you do in many of your cases. Fine. So, but since x max has been modulated, like absolute value has been taken, but this can be positive or negative. This can be positive or negative. See, x can be x max, right? Am I correct? If x becomes x max, what is x prime? 1. Okay. If x is 0 or x min, like maybe 0, say minus, how we can say it is going to -1, like it can go to +1. You can see, like if you take x equal to x max, x prime is +1, isn't it? So if you take x min, how you can get it -1? Like how I am telling over how I am claiming, like 1 is understood, how -1 is obtained? That's my question to you. X equals to minus, yeah, x equal to minus x max is one of the good candidates, but can we guarantee that minus x max is the minimum one? I mean, yeah, that can be correct. Can be correct. There is no other way we can get -1. So I want to ask how it can go to -1. We saw if you take the maximum quantity, you divide by the max, it will go to 1. But how you can get -1? No, if you take x to be 0, it becomes 0. X prime is 0, right? And 0 lies in between -1 and 1. That's fine. I mean, 0 can lie in your data. So x has to be a negative quantity. X has to be a negative quantity, of course. If x prime is -1, suppose, let us analyze a bit. Suppose x prime is -1. So which has to be negative? Can the denominator be negative? Denominator cannot be negative. So the only way the quantity can be negative is for the numerator to be negative. Now the numerator has to be negative in such a way that it cancels out the maximum, right? So it has to be a minus x max. But my question is can it be more than, like, less than -1? I mean, how can we understand that minus x max will be the last one, like the extreme one? That's my only question. Okay. So as usual, some things you have to think. I will give it to you. Okay. So try to think like minus x max is the particular candidate, but why it is the candidate? It can be a candidate. Mind my words, it can be a candidate. A means many other candidates are possible, but I am saying it is the candidate. The candidate means no other candidate can give you -1. It is the only candidate, minus x max, right? So there is a difference between a and the in scientific disciplines. So whenever you read anything, make sure you read them properly, where the is written, where a is written. Okay. Okay. Another one is known as the decimal scaling, right? So what do you mean by decimal scaling? The same thing I told you, like maybe the number, yeah, we'll see an example anyway. So you take a number here, the variable, and you divide by some multiple of 10, like some power of 10, 10 to the power j. So one question is, what is j? What is j? Okay, j has to be decided. J has to be decided. So j has to be a quantity such that it can result this quantity. That the maximum of modulus of that transformed quantity has to be less than 1. Okay. So we will see an example. So you can take this example over here. It's worked out. So you can take this data set, simple data set for you, 12, 345 and 6789. Okay. So what's the max here? What's the max of a? So you can see 6789, right? Now, can you find a value of j such that the transformed value will be less than 1? That means 6789 divided by 10 to the power j should be less than 1. You understood, right? See, what power of 10 should I divide 6789 so that the quantity 6789 divided by that quantity is less than 1? Can it be 10? No. 10 square? No. 10 cube? It will be 6.789. 10 fourth? Yes. If you put j equal to fourth, it will result into 6789 divided by 10 to the power 4, which is 0.6789, and it is less than 1, right? So you can see this is known as decimal scaling. Okay, this is known as decimal scaling. Such a big data value like 6,789, you transform to just 0.6789. Okay, and the quantity less than 1. So you can see over here, the same thing you can do. So you will have to apply this in all of your data elements, right? So your data set consisted of 12, 3, 4, 5, 6, 7, 8, 9. This is the A data set. Then the transformed data set via decimal scaling will be 12 by 10 to the power 4, 3, 4, 5 by 10 to the power 4, and 6, 7, 8, 9 divided by 10 to the power 4. So this will come in decimal things, like you can see 0.0012 and same as written over here. I hope that is okay. So, and you can clearly see here all positive values I had taken, but you could have taken negative values. Suppose it is -12. So it will be -12 into 10 to the power -4, 10 to the power 4, minus 0.0012. But still it will lie in between -1 and 1. Still it will lie in between -1 and 1. That's the idea. Okay. So all of your scaling will lie in a standard scale. So that's the idea of scaling and normalizations. One good thing about this is it doesn't change the distribution of the shape of the data. Okay. Do you understand why? I mean, are you getting why? Yes, yes. I mean, just scaling. It's just a scaling. Like it can either like zooming in and zooming out. It's the same thing, but the same shape will be preserved. Same shape will be preserved, right? But it's just like scaling also. Like you can just think of like this x square function, and you just, this is x square, y equals to x square, and you just shift it by 2 plus 2. So it will shift up. If you do -2, it will shift down, right? So same ideas you can, apply over here. Anyway, so These are the ideas. Okay. One important, let us go to the Z score because one more example was there. I forgot about that. So this was the second question. This was the second question. Like, so using Z score, here you will see Z score normalization. Suppose the mean and standard deviation is of the income value is given to be $54,000 and $16,000 respectively. Then with your Z score normalization, what this value of 73,600 will be transformed to? What value of income $73,600 will be transformed to under the Z score normalization, given that this is the mean and this is the standard deviation. So what you have to do, nothing else, just you know what is the Z score over here. So this is x prime. X minus mu by sigma, right? So mu you all, sorry, x is what? Yes, that's the value it is being asked for which transformation for you to make, right? What is the mu? Mean is 54. Okay. 54,000. Then you have to divide, just you can see 16,000 over here, and you get your value here. Okay. So you can see the Z square is not in between -1 and 1. Z score has gone beyond 1. Why? This is the part I want you to like just understand a bit. In all other cases, like in your min-max normalization is always in between, yes, 0 and 1. But Z-score normalization is not like that. Whereas decimal scaling will be in between -1 and 1. But why Z-score normalization is a quantity which went beyond 1? I mean, no one will ask you much detail about this, but it's good to know. How? Like, I mean, multiple standard deviation. Yes. So you can see standard deviation is 54,000. Yes, that's. So can you see from the previous class when we say is an outlier? Okay. So you can see when it is an outlier. 3 times. 3 times the. Yes. So can you see the mean is 16,000, whereas the standard deviation is, sorry, the mean is 54,000. Standard deviation is 16,000. So how? Standard deviation is less. It's good. I mean, the previous batch I showed the same example, but this kind of discussion I never had. So it's quite good that you're discussing. So I suggest try to understand this example. Yes, exactly. Exactly. So therefore we told it like mu plus or minus 3 sigma. Mu plus or minus 3 sigma, right? So if from that you can at least understand why its value can be 1.225, right? Go back to your Z-score normalization class. Go back to your Z-score normalization class. So hmm? Okay. So this question is important. This question is important. Okay. So I suggest like please go through this question again. So this question can just connect. We can ask you in the finals, like this is the question: find the Z-score normalization, and what can we do? What can we do for this? Okay, what can we do? Like why Z-score is beyond 1, and what insight can you get from these two variables regarding standard deviation? Okay, so this connects to the last class I told you about. So think about it. Okay. Now let us come to something known as encoding. Okay. So now we have understood what is binning. We understood about feature scaling, what kind of different types of scaling you apply. Like you can apply min-max normalization or min-max standardization normalization techniques, robust scaling, decimal scaling also you can apply. Okay. So there are many different cases you understood, like why we have this z-score normalization, why we have this robust scaling. In z-score normalization, you subtracted by mean, whereas in z-score normalization, sorry, okay. So encoding categorical variables. So let us come back to this scenario now. What is encoding? Okay. So how to deal with categorical variables? This section is about how to deal with categorical variables, because most of your machine learning algorithms will be dealing with numerical variables, right? Weights, numbers, and all sort of things. But they won't be dealing with categorical variables. So how? But you need categorical variables also. I mean, suppose using machine learning techniques, you take the retina image of all the students, and you want to classify the retina image of all the students into different class. Maybe brown, maybe black, maybe green, maybe reddish. Okay. So, yes, I don't know. So, you can classify. So, how the machine learning algorithm can classify it? It will be reddish, greenish, brownish, or all these are categorical variables. So you have to assign some numbers to it or some series to it so that one can understand, right? So therefore you have to encode those categorical variables. So therefore we have this topic known as encoding categorical variables so that we can work with categorical variables without, I mean, it's a way of conversion. Okay, it's a way of conversion. So in many data sets, some features are categorical instead of numerical. Okay, example, you can see the colors, city names, product types. Okay. However, most of the machine learning algorithms only understand numbers. They don't understand any text, right? So how can you do that? So only one idea is to map these categorical values to numeric values. Okay, and this such type of process is referred to as encoding categorical data. Okay, the way of converting or like mapping. Okay, I would say the correct technical word, mapping the categorical variables into numerical values, and this process is kind of called like encoding your categorical data. Okay, so how to do that? There are two types. Okay, and why it is important, you can see they require numbers. Okay, and algorithms like support vector machines, decision trees, neural networks need numeric inputs. Okay, uh, of course, you can see while clustering using k means you will compute distance between two clusters. So that way you deal with numbers. Linear regression and PCA cannot work with strings. So you work with the matrices in PCA. You find the dominant eigenvalues in those cases. So numerical features you can see is easier to interpret and scale. So encoding, like this, after encoding known as the encoded data. So encoded data lets us apply feature scaling, what we have learned just now. Like you can apply the normalization, min-max normalization, decimal scaling, all sort of things, and do various statistical analysis possible. So one kind of encoding is known as the label encoding. Okay, label encoding. What is about label encoding? So you can see assign to each unique category an integer. To each unique category, you assign an integer to it. Suppose you can say the colors are there, red, blue, and green. So these are categorical variables. What we do is assign a number. Assign a number to it. So the encoded looks like red can be assigned number 0, blue can be assigned 1, green can be assigned 2. But it is okay, it is simple and efficient. So if I mean 2, then I can easily color them green, right? And I mean green, right? Green color. But one disadvantage is it can mislead your data set. That means it can tell you that since green has been allotted the value 2, it means the green value holds more importance than the red which is assigned 0. So sort of ranking you might think. So you can think like green is better than red, like shown in the slide. So it will mislead you thinking that it has an order to it, which is not the case. Which is not the case. So we will see when you have an order to it, when you have an order to your encoding, it is a other kind of encoding, other type of encoding. Okay. If you don't have such orders, it is known as label encoding. Fine. Another is one hot encoding, quite well known. So yeah, one hot encoding, you can see instead of just assigning values, which can create a confusion of the rank. Like if you assign a value, suppose green is 2, like we did in the previous slide, it might mislead you to think of it as a rank. So instead of that, what we can do, assign as a vector, like a binary. So now I hope you know that who uh, uh, this universities. In universities are being graded using NAC. Universities are graded using NAC. Now, different universities were being graded like A plus, A plus plus plus, okay, A, B plus, something like that. But now this year, from this year onwards, they started to do binary, binary. Those who got 1, okay, those who did not get 0, something like that, like binary NAC. So NAC has followed that strategy over here. Okay, so you can see that therefore this is the idea. Like if you assign 0 and 1, it doesn't convey you an idea of ranking, but you assign not a number but rather a column to it. So how to do that? So you can see red, blue, green is there in our color set. So one hot encoding, what it does, it will create one column for each of them, and the number of rows will be equal to the number of elements. So you can see the number of elements here is red, blue, green, 3 elements, and therefore there are 3 columns for each of the data element, and there are 3 rows also. Okay, there are 3 rows also. So you can see red is allotted 1 and other elements are 0. Blue is the second one, 0, 1, 0. Green, 0, 0, 1. So if you mean 0, 0, 1, it will just go to green. It will not provide any sense of ranking over here. So you can see avoids false ordering, and it is widely used. And even one disadvantage is if you have lot of like big data. I mean, we'll learn about big data also today if time permits. So if you have a large data set, then more number of sparse like columns you have to add, which is kind of tricky, right? I mean, it will grow in size exponentially. That many number of columns you have to deal with. Okay, so only the problem is with data set dimensionality. Might not work that much efficiently if you have big data. This is the ordinal coding encoding, which is similar to the label encoding. Okay, in label encoding, you were not having any rank, but in ordinal encoding, you will have rank. I mean, it has a natural order to it. How? Well, let us see. It is used when your categories have a natural order to it. For example, small, medium, large. Suppose you uh, brought your costumes or something like that, and it has size to it. Small, medium, and large. Like small, you can assign 1, medium, you can assign 2, large, you can assign 3. So if I assign 3 value, I can easily understand that it is the large, I mean, large dimension of the costume for you. So it preserves an order to it. You can see, you can compare this with uh, label encoding, right? So label encoding doesn't have this. Label encoding just gives the number, but it doesn't have any order to it. I mean, green is greater than red. It is meaningless. Okay. But yes, large is greater than small. Yes, it is meaningful. Okay. It is meaningful. It has a natural order to it. However, for colors, like those who don't have any order to it, it is not meaningful. Like colors. If you have colors, categorical variables, like you can apply label encoding. If you have a categorical variables where natural order is there, like grades also, okay, a excellent, A plus, something like that, then it has a natural order to it. For those variables, categorical variables, you can use ordinal encoding. Those variables which have order to it, you can use ordinal encoding. Those variables don't have an order to it, you can use label encoding. Okay, is that fine? Or I mean, very, I mean, intuitive ideas. Okay, but has meaning to it. Has meaning to it. So these tiny things will only be connected to you when you are trying to learn about machine learning or some algorithms. They will just, while learning some machine learning algorithms, like they will just tell you, we use one-hot encoding, something like that. Then you will be surprised. What is one-hot encoding? So that you learned here. So some tiny terms will come when you are reading. So it will be helpful. Something known as derived features. What are derived features? That's one of the concern here. So derived features means you derive it. Okay, it's not the newest one, it's you derive from the existing ones. That's known as derived features. So derived features are the new features which you create from the existing features. Okay, so one of the examples we will see towards the bottom of the slide. You can see they add more information. Of course, the derived feature will add more information as compared to the existing features. Okay, so you can see these derived features, they help the machine learning models to capture the hidden patterns in your data. Okay, so you can see raw data is there. Some raw data. These are the existing features. These are the existing features, and you apply some transformation and you create new features with more meaning. These are derived features. These are derived features, right? I hope okay, that's okay. We'll see an example, no need to worry. Like you can see, I took the weight and height of every student over here. I took the weight and height of every student over here because I am interested to compute the BMI of each student. Okay, what is BMI? Yes, body mass index. So the people, like it tells us whether the height, people with more height, they usually have more weight. Okay, because of the bone density. The people with less height, they usually have less weight. Yes, they have less weight. But if this is not followed, I mean, if higher, like taller persons have least weight, I mean, less weight, then their body mass index is, of course, not good, in the not good side. Okay, so therefore, you have to maintain your BMI levels. So you can see the weight and the height are the existing features of the data set. Okay, you understood the weight and the height are the existing features of the dataset. Now I am applying a new transformation, that is the BMI over here. Okay, you can hope you can understand. You can apply BMI. How? How I can apply the BMI? Using weight and height. You can see the formula over here. Weight divided by the height square. Weight divided by the height square, right? So weight and height are my old features. I applied just a transformation, that is weight divided by height square, and I created a new feature, that is BMI, right? And this feature is more meaningful than the past features of weight and height. Okay. So, yeah. So you can see, like, it improves, it captures the relationship. It captures the relationship between variables. So yeah, it makes data more interpretable also. Like instead of weight and height, which you would have looked, oh, the weight is high, is the height more? No, is the height more? So manual you are preventing. So just one transformation can help you understand a lot of different features. Okay. So this is known as derived features, right? Fine. So I hope now in this class you're understanding tiny things. Okay, tiny, like what you understood so far. Binning was one of the concepts we understood so far. Any next one? So how to handle skewness? Okay. Then feature scaling. Yes. Like what do you mean by decimal scaling? What do you mean by normalization? Min-max normalizations. Okay. What do you mean by robust scaling? Then encoding. What are the different types of encodings? Okay. Then what are derived features? Okay. One hot encoding, dummy encoding we learned. Okay. What are derived features? Okay. What are derived features? Features which are derived from existing features, but they also convey something, some important meaning to your data set. Okay, like weight height was there, but when you applied a transformation, you got BMI index. And BMI index can provide you much more information than weight and height alone, right? So you can see BMI is a derived feature, which is created, which is derived from the existing feature of weight and height. Okay, till that we are in this class. Okay, now let us come to the next topic, that is data reduction. Okay, so yeah, of course you know that if you have a very big data set with you, of course, like it will take more computational power to go through the data set and process the data set. So therefore you have to only choose how, so you cannot discard all the values of your dataset, because you will lose the most important parts of your dataset. So you have to choose the most important ones, most important features of your dataset, so that even if you take those features, it will represent almost similarly to the old dataset, right? So that's the idea. That's the logic behind this. Okay, that's the logic behind data reduction. I mean, you cannot say that we have this full class. Okay, we have so many people over here. Let us eliminate this column and that column. No, we cannot do that. Okay, because there are many persons over here who know, who are willing to grasp the concept easily. Okay, so like that. Okay, so don't we'll not eliminate those people. Okay, it's not that game. Okay, not that game. Anyway, so uh, so you can see it can be applied to obtain a reduced representation of the dataset that is much smaller in volume, yet closely maintains the integrity of the original data. If you have made your dataset reduced, it doesn't mean, like, if you eliminate data elements from your dataset, it doesn't mean your dataset is reduced. The reduced dataset should reduced dataset should follow the same or similar pattern as the original dataset. Unless that happens, it is not a good reduced dataset. Okay. So you can see there are various steps to it. So data cube segregation, data cube aggregation, all those concepts we saw previously, right? I hope you remember that cube, and we were thinking what each of the columns, rows of the cube means, how we aggregated different cubes together. Okay, I hope that is okay. We also understood, like, we have not understood, this is one is left for future, sampling. Okay, so I will just give you an basic idea today. Okay, and there are many different important sampling methods. What is sampling? Sampling is like I don't know. I don't know why my oh, this is itching. There is something known as attribute subset selections also. So these two methods we will learn after your holidays, but I will cover sampling today. Just a basic idea. Okay, what is sampling? Data sampling. So data can be big. So can we make it so the data is big? Data can be big. So how, then the question is, can we make it? Can we make it small? Can we make it small by selecting some part of it? Okay, can we make it small by selecting some part of it? So data sampling is the technique to do that. Okay, so sampling is the main technique employed for data selection. I mean, which important data features to select so that it represents the original data, right? So one good idea is this: you have the big data, right, with different features. So you can see different colors imply different features, right? So the sample data is this. Maybe this one you selected this and this, right? Then two times this is selected, then one of this. But you are missing out these values, right? So the question is, does the sample data kind of represent the distribution as that of the original data? Unless that happens, it is not a good sampling technique. Okay, fine. So you can see the statisticians, they sample because obtaining the entire set of data of interest is too expensive. Here too expensive means both numerical computation and computational power. Okay, you will see that there is something known as big data, right? And big data cannot be handled by just your laptops and normal computers. Okay, so and time consuming also. So one example to ask is, what is the average height of a person in India? So you cannot measure the height of every one person. Okay. So sampling, therefore, is a technique used in data analytics because processing the entire set of data of interest is too expensive and computational time consuming. Suppose another example, we have 1 million documents and we ask the question, what fraction has at least 100 words in common? Okay, what fraction of number of documents has 100 words in common between them? So that's very, I mean, you can feel that question, right? How complex the task is. So if you compute using your like probability and what do you call that, permutation combination, so you can find that around 10 to the power 12 comparisons are needed, which is pretty high, right? So therefore, while dealing with big data, you have to use the sampling technique very intelligently. And for that, there are different sampling techniques. Okay. Okay. So what happened here? Okay. So you can see that using a sample will work almost as well as using the entire data set if the sample is representative. So considering any sample is not the idea. Considering the representative sample is the idea. Okay. So when can you call a sample is representative? When you call a sample is representative. So you can see a sample is representative if it has approximately the same property of interest as that of the original set of data. So this line is a very basic line. I think everyone should understand this line. Okay. Otherwise, we say that the sample introduces some kind of bias. And so the question we ask like is, when you see a bias is something like this. What if we take a sample from the university campus to compute the average height of a person in Tirunelveli? That is some wrong, right? I mean, this university number of students, the height will not represent the height of people in Tirunelveli. So considering this sample is not a representative sample. So you can say when a sample is not representative. So I hope that is quite clear. Hmm? Okay. So anyway, so there are different types of sampling. So yeah, one is simple random sampling. Okay. So they, what do you mean? Like if you have a box of like many coins, okay, 1 rupee coin is there, 5 rupee coin, 10 rupees coin, 50 paisa coin, not now, but they are suppose. Okay, so many things are there. So when you choose any coin you like, so there is randomly. So everyone deserves an equal probability to choose, to be chosen, right? Yes, head and tails have 1/2 probability to occur. Sampling without replacement. What do you mean by sampling without replacement? You suppose you took, maybe there is a pink coin here, okay, and you took that coin, you chose that coin, okay, and you keep it. I mean, you don't replace it. You don't replace it inside the sample again. So when you choose another coin, the pink coin won't be there. We can say that for sure, right? Because you took that pink coin already. Are you understanding? You are not replacing the coin back. You are not replacing the pink coin back. So without replacement, sampling without replacement. So therefore, the pink coin won't be there, right? Good. So each item is selected, it is removed from the population. So here the pink coin is removed. Sampling with replacement, what does it mean? You took the pink coin out, okay, and when you again choose a point, you replace that pink coin back into the population, right? So observe the difference that you can choose, the chances of choosing the pink coin can be there now. Pink coin can be chosen more than one time. Are you able to understand? You understand the difference between the two? With replacement means I took the pink coin out, then I took another point, then I should put it back inside the population. So first time I already chose the pink point. Now since the pink coin is already there now, again in the population, again it can be chosen. Okay, so it can be chosen more than one time. Whereas in sampling without replacement, pink coin is already out of the population and it won't be fed inside the population again. So when you choose another coin, it will never be there. So you can never choose it. Is it okay? That is what it is with replacement. I mean, there are some experiments like that. There will be experiments where you have to follow these two. I mean, there will be experiments where you will replace it again, right? You can think of some applications. This is a good exercise. Can you think of some good applications where you can apply sampling with replacement and without replacement? I mean, it is a normal strategy. If you took a coin out, why again you will put it back, right? But there are some practical scenarios where you have to put it back because that's how the uh, situation is designed. That's how the game is designed for you, right? Anyway, so stratified sampling is also there. So you split the data into several partitions and draw random samples from each of the partitions. But out of all this, there is another important class of sampling technique known as reservoir sampling, okay, which is very much important. So, which is very much important, and I suggest that one of your students, like in the class, should give a talk on it. Reservoir sampling. Last, like you can give an example based on the shuffling technique, like Fisher-Yates shuffle. So you can take this example, and here you can see reservoir sampling being applied. Okay, reservoir sampling, and one of the most important sampling techniques. So I suggest, can one of you, is it okay if one of you can give a talk here? Because last 2 years, everyone has taken this as an assignment and given a talk in the class. So let us come back. Okay, let us come back. Like, what do you mean by data integration? Okay, what do you mean by data integration? So you can see, like, what do you mean by data integration? Like, you have data from different sources, right? I mean, I can tell you that suppose you have, maybe I can consider one of my examples. Can you give me one example? I want a real example. I mean, data integration. A body shop, suppose. Okay, you have the body shop here. Okay, so there are many different branches of the body shop, right? I mean, in Trivandrum, you will have one body shop, B1. Maybe in Kalakutam, you will have the second one. Maybe in other places, you will have different branches, right? Now they want to analyze the sale. They want to analyze the sale of these bodies over here. Okay? But only in Trivandrum it happens, right? That it's famous here only. So what you do is, all the data sets has to be given to the owner who is managing the central shop. This is one of the central shop, right? So what he will do, he will provide, all the centers will provide data to him, all the shops will provide data to him, right? So they will collect the data and store in a unified format. The problem lies is, like, maybe each of these shops are storing data set in a different manner. Okay, in a different manner means, maybe it can be, I mean, if it is an efficient shop, it won't do. But if they don't have this analytics ideas and knowledge, then they might not be knowing more and give more respect to these techniques. Okay, what will happen is, bully shop will store like this, B1 will store like this, like no name of the customer, only mobile number and how many units he has taken and what's the profit for each of them. So this customer took, okay, this customer took some 2 units of boli, and it profit made is around 70 rupees, something like that, right? So you can see this is the data. Maybe boli 2, what it will do, it will not store the mobile number, but rather it will store their, maybe credit card details or credit card, like, because maybe someone will pay in credit card, right? So they have the credit card numbers or data of that. Through this you can get the names and all the things, address and all, right, using credit card details. So but this and this are two different things, so how it can be merged together, right? When you give this to the central boli shop, how it can merge or integrate the data, because this column is not equal to the credit card column, right? So what it can be done is, you have to add one column known as name or mobile number in a unified way, so that you can integrate the data together, right? I mean, this is just one of the examples where you can feel that the columns of your data set are not same, and therefore if it is not same, you cannot unify your data. So this presents the challenge for data integration. If you combine the data from multiple sources and combine them together, it is known as integration of your data, right? So you face multiple kind of problems, like integrating metadata from different sources. To know more about the metadata, I can give you one example. Like when you go for an MRI, you see a very black and white picture, right? You see a very black and white picture. Do you know what it is called? Do you know what it is called? It is known as dicom. It is known as dicom. So it's a dicom image. What that image? That image is not just an image. That image you are seeing, that MRI image is not just an image. That image inside that has already coded features, okay, and attributes. Okay, it has indirectly coded who is the patient, okay, what is his age, all details of the patient, and what he is suffering from, what diagnosis it has been given. The DICOM is not just a JPG file; it is a metadata. It is a JPG file plus metadata. What are the metadata? Like what is the information of the person? What is all the details? Means if you have the DICOM image, you can get all details about that patient. You can get all details about that patient. So therefore, you have to preserve these DICOM images so that DICOM images cannot be misheld. I mean, if it gets leaked, then all privacy of the patient is lost. So in that way, data is so much, you need privacy, right? I mean, you have to protect privacy of your data. So DICOM file is one such file. I mean, like this kind of health issues and all are very sensitive information. I mean, if some big VIP person is there and you got the idea what he is undergoing a surgery on and all, then the whole plan will change, right? How to take part of in that, so many things. So these are kindly related in many places. So just an idea from a real perspective. So one of the master students also worked on encrypting this DICOM image. Okay, if you have various DICOM images with metadata, how you can encrypt those images so as to preserve your data. Okay, so I can show you in some class. Okay, so yeah, so you can see there can be different issues, like maybe in one file Bill Clinton will be there, in another file William Clinton will be there, but it's almost the same. It's almost the same because they might be family members. So it's almost representing the same family. Okay, so it should not be represented as two different data. Okay, so that's the challenge you face in data integration. Okay, so I'm giving you some challenges, how to handle them. So drop duplicates. If you see multiple duplicates, you drop them. So this is how you handle redundancy in your original data set. Okay, using data integration, while performing data integration. Okay, so redundant data, like you can of course see that maybe the same person name will be there in multiple data files. Same person name can be in multiple data files, but you need only that person name once in your final data file. You cannot make them four rows or four columns for that, right? So that's how you have to drop the duplicates. That you can do in Python using drop duplicate commands. Okay, drop duplicate, and even you can use drop NA command also. Okay, this I will make a separate lecture for that. Okay, and give you. Okay, what is a series? What is, how you can group by operations? How you can group by according to age? Okay, so if you see the same age and the similar name of the person in multiple fields, then it's redundancy. But how will you know that? This is the technique, but how will you know that in a data set? You have to group by. You have to group by according to the name and according to the age. If the name is similar and the age is also same, then you are very sure that yes, this is the same person, but we are framing it as a different person. So that's a redundancy. So instead of that, only one row will suffice, right? So that's how you handle the duplicate parts. Okay, fine. So I mean, same things repeated here. Like you are getting data from multiple sources again and again. You reduce and avoid redundancies, inconsistencies in your data. So which can improve your data mining speed and data mining quality. Okay, which can improve the data mining and data speed quality. Okay, fine. So this is all about data integration. I told these tiny topics to you so that you know these names. Like there is something known as data integration, there is something known as standardization, normalization, something like that. Okay, so these terms won't be new to you. That is the idea of this lecture. Okay, okay. So yeah. So now the idea is like we will move to wavelets. Okay. Now, and we will see a real world scenario. I will show you a web page also where they have shown very nice example of wavelet transform, discrete wavelet transform to compress your images and denoising your data. One of the practical examples of how to denoise your data is discrete wavelet transforms. Okay, you can we will see why you cannot use Fourier transforms. Why you cannot use Fourier transforms? Yeah, why you cannot use? Hmm? Okay. So, we try to understand about real world data and real world signals. Okay, how the real world signal look like. So actually, real world data and signals, they frequently exhibit slowly changing trends. Okay, or oscillations. Okay, with some transients. Some transients, like what does it mean? Like one of the examples is like maybe when you wake up. Okay, when you wake up, like when you wake up, like these are the transients. You just don't start doing work, right? You sit for some time, and then when your brain fades up, you are in real world, then you start doing your things. Okay, so that's one example. Okay, so these are the transients. Even when you come to the class, you prepare yourself, you take some time, 1 2 minutes. So those are the transients. Okay, so transients are not the actual cases, they are the first few random iterations or random cases. After that, your data behaves in a proper way. Okay, so in every case you will have transients, and you have to discard those transients because the transients doesn't represent a part of your process. Okay. Okay, so you can see when you consider different images, suppose you have different images and these images have some smooth regions, right? I mean, if I take an image of this class, then there are smooth regions. What are the smooth regions? In between the road here, like the path here, these represent the single color. Whereas your branches over here, all students are wearing different clothes. So it's different. So it will be a jump. It will have a jump from one color to another color. But if I asked that everyone wear the white color shirt or something like that, then all will be in white colors. So there will be two distinct colors. It is either brown or white, right? So therefore, but rarely that happens. So therefore, in images, you will find sudden jumps in color. And usually those sudden jump in colors in your image represent the most important part of the image, isn't it? That's an example we will see. Okay. So therefore, you can see the third point, these abrupt changes in an image are often the most interesting parts of the data, both perceptually and in terms of information they are providing. Okay, so we'll see, don't worry about it. So the Fourier transform is a powerful tool for data analysis. However, it doesn't represent abrupt changes effectively. Okay, so therefore you don't see Fourier transform being used in many of your data analysis techniques. I hope you remember that Fourier transform is the sum of sine waves. Fourier transform is the sum of sine waves, infinite sum, in fact, right? So there is the sine term just oscillating again and again infinitely, right? So therefore, you can see the reason is that Fourier transform represents data as a sum of sine waves which are not localized in time or space, and these sine waves can oscillate forever. Okay, so this is the reason why you don't normally see Fourier transform being used. So how to accurately analyze these signals and images? Those have abrupt changes because that's the way images are being clicked, right? And see, like if you take a sunset image, right? So sun will be there in that image, and there will be different waters and all. So blue will be there, orange will be there. So there is a sudden jump, and this sudden jump is important because they classify the transition from the sunset to your river side, right? They capture the most important part of the image. I mean, I hope you understand the logic behind this, right? So therefore, how to do that? So we need to use a new class of functions. Okay. So we need to use a new class of functions that are well localized in time and frequency, which was not the case in your Fourier transform. Okay, in Fourier transform, it is not localized in time and space like that. So, and it represents the sine waves in an infinite way or infinite oscillations. Okay, so therefore, this brings us to the topic of wavelets. Okay, this brings us to the topic of wavelets, and we understood why Fourier transform doesn't work. Okay, so wavelet, because wavelet might remind you of Fourier transform, so I cleared the air that Fourier transform is not usually used. Okay, Fourier transform is not usually used. So let us see what is a wavelet. So I have taken this from the MATLAB web page, but it's a very good resource. I will share that to you. So you can see this is a wavelet. What is a wavelet? I mean, you know about sine waves, you know about discrete Fourier transform, okay, Fourier series and all those things. But wavelets is something very nice. What is a wavelet is, you can see wavelet is first a rapidly decaying wave-like oscillation. Okay, of course it's a wave-like oscillation, but it will decay to zero. That has zero mean. That has zero mean. So you can see it is perfectly symmetric, right? It is perfectly symmetric around here. So you can see the left in my red boundary line vertical, it is just a right and left copy of it. Okay. So wavelet is rapidly decaying wave-like oscillation, which has zero mean. Okay. Unlike sinusoids, which extend to infinity and oscillating every time, wavelet can exist only for a finite duration. Okay. Wavelet exists only for a finite duration. And this is why you can, approximate most of the real world signals using wavelet, right? You can approximate most of the real world signal using wavelet, because you can apply wavelet to the part of the region where you just want to understand the data or the signal about or the time series about. Okay. So there are different types of wavelets which come in different sizes and shapes. So you can see, just for your understanding, most commonly this is being used actually. So Dobich is a wavelet, one of the most common example of wavelets. You can see different, graphs of the wavelets. You can see. So wavelet is not only very nice looking sine things. It can be rough as this also. It can be this also. It can be something like a square sine wave signals also. Okay. To choose the right wavelet, you need to consider the application you want to use it for. Okay. So every wavelet is designed and is useful for a particular set of applications. But to be honest, in my fields, I have seen this one more prominently. Okay, but many other people, many other scientists and all, they see this wavelet quite frequently. Okay, this wavelet quite frequently, right? So every wavelet has a scaling factor, okay, and a scaling, and every wavelet has a scaling factor and a frequency, right? So how you can decide like a wavelet according to their scaling factor and frequency? Okay, what is the frequency of a signal? Any ideas? What is the frequency of a signal? It's like 1 by time period. 1 by time period. Time period means after how many iterations the same value is reached again, right? After how many iterations the same value is reached again. Okay. So you can see this is like a 10 hertz sine wave, and when you scaled the sine wave by factor of 2, it became like this, and it became a 5 hertz sine wave. You can see less frequently it is oscillating now. The second part is oscillating less frequently as compared to the first part. The first part is oscillating very high frequency, right? I mean, in a tiny branch of interval, you can see multiple oscillations. In this part, suppose maybe let us see from this part to this part, right? In this part to this part, you see how many oscillations? At least the dip is around 2 dips, right? But here, the same width if you take, like maybe we'll just, yes, you can see just only one dip. You can see just only one dip over here, right? So that's how the frequency has decreased now. I mean, less oscillations it is undergoing. Okay. So this is, if you scale your signal, the frequency is reduced by half. So frequency is inversely proportional to scaling. Okay. If you scale the signal, the frequency also reduces. you scaled it by a factor of 2, so your frequency reduced by a factor of 2. So frequency you can see is inversely, scaling factor inversely proportional to frequency. So when you scaled it by 2, it reduced by half, 10 by 2, that is 5. Okay. So try to, just imagine a bit. I think like maybe this data might be a bit, is it hard for you or something? It's hard. It's, it's hard, right? Bit, a bit. Okay. Maybe what I can do is not go too deep onto this, and I will just show you the application of this. How about that? I mean, we'll not go too much detail about this. I mean, just the application about this, not worry about much of frequency and all this. Anyway, so this is an idea like if a stretched wavelet, like this is a good example, and I think it is important for you, even though not much math is involved. Anyway, so a stretched wavelet can capture your slowly varying changes. Okay. So in these two cases, can you say like which wavelet can you see this? There is some changes there, right? Where I've circled. In both cases, it's the similar thing, but which wavelet can capture the most important information? Is it the left one or the right one? If you see the left one, it is not able to, it is just able to capture some of the points. But if you see the right to wavelet, it is able to capture more of the points. It is able to capture more of the points over here, right? Isn't it even here? Many points here. So you can see that if your wavelet is stretched, understood? The wavelet is stretched. How it will look like? It will look like this. Wavelet is stretched. Okay. If a wavelet is stretched, then it is not able to make the use of highly frequently occurring signals. I mean, highly rapidly changing signals. If you have high frequency signal, that means a compressed wavelet. That means a compressed wavelet means like lot of frequency like this you will see, which you see over here, right? High frequency. Then it is able to capture those slowly varying, highly varying changes, right? So this is a important example as to understand which wavelet can help you understand which kind of signal. Okay. I mean, a stretched wavelet is not a good idea to understand your abrupt changes. This is an abrupt change, right? Is this an abrupt change? Is it fine? This is an abrupt change, right? Suddenly it got spike. Now, in order to capture that abrupt change, there are two questions. Will you use a stretched wavelet or will you use a high frequency wavelet? Yes, that's the idea. If you choose high frequency wavelet near that abruptly changing signal, then you are able to capture most of the information of that. Whereas if you use a stretched signal, you are not able to capture that abrupt change. It is visual proof over here. Okay, it's a visual idea. Okay, and I think this is the most important one. We will not cover any more things. Okay, but I will try to show you where discrete wavelet transform can be used. I mean, discrete wavelet transform can be used. Okay, so you can see the left image is the noisy image. Left image is the noisy image. No, can you see some amount of noise over here on the left image, right? So you can see a lot of tiny dark pixels are occupied in the lion or the tiger. I don't know. Uh, image. Okay. So you can see after you, oh, good. Okay. After you apply discrete wavelet transform, it can remove the noise of it. I mean, still the noise is there a bit. I mean, still the noise you can see in this image, but it has reduced, of course, no? I mean, two different images you can see over here, right? So this is how discrete wavelet transform can help you in denoising image and data compression. So data compression we will see using one algorithm today. Okay, we'll see that. And you see this is another example over here. This is the original image. You can see the axis over here. Axis numbers are there. Okay, and this is the compressed image after using the discrete wavelet transform. Discrete wavelet transform means you are using one of the wavelet transform I told you. That is the Dobbechi's transform, that is 3-4 transforms I mentioned. One of them you are using here. Okay. So after you use that, this is the compressed image. Of course, you can see that the compressed image has a bit less quality than the original image. I hope you can see how sharp the left image is, but how it's a bit blurred. This image is a bit blurred, right? So you can see that this part is quite easily seen very brightly, but not present here, right? So I hope that is quite understood. And this is the compression ratio, like 1.65 percentage ratio compression you do. This BPP and all more you will understand once you go more deep and deep inside this discrete wavelet transfer. So I will show you a web page where you can see that. So mm, so you can see this is I will share you the link, and this is quite interesting, like wavelet denoising. So this example shows how to use wavelets to denoise signals and images. Okay, so this is MATLAB. It is another language. Okay, MATLAB stands for Matrix Laboratory. Okay, Matrix Laboratory, and MATLAB is quite popular when you handle high quality image, high resolution images. Okay, whereas Python doesn't work that well in those cases when you have high resolution images at hand. Okay, and the MATLAB treats everything as matrix. MATLAB treats everything as matrix. Whatever you have, it will treat as a matrix. Okay, so it's a matrix laboratory, and you play whatever you do. You create an array, you create plots, everything. It's a matrix. Okay, so they have shown using the plot here. Okay, they are adding. You can see this is a white noise. W noise means a white noise, and these are the parameters of that white noise they are adding over here. This is the original signal, and after that, this is the noisy signal they are plotting. You can see this is the original signal over here. Don't worry about the x and y axis. Okay, might be a time series data. X axis may be a time. Okay, and this is the noisy signal. Like you can see, the noise has been there, but you can see it almost representing the part of the original data, isn't it? It kind of represents the original data, isn't it? Like you can see the bump over here. The bump is still there, but it is more oscillations and noise, right? So you denoise the signal down using this kind of wavelet transform, that is WDE, not denoise, WD noise, that is wavelet denoise. Okay, and this is how it looks like. I mean, suppose you have this original signal and this is the denoise signal. I mean, they could have used some other color to differentiate, but it's fine. You can go through this. Okay, so let me show you the last one. Yes, you can see this is the noisy signal. It is noisy. It is okay till here. Okay, but it is a noisy signal. And after you apply the wavelet, you get the signal like this. So it has removed the noise from the signal, right? It has removed these unwanted oscillations in your data set, right? So you can see now it is a very clean signal. Hmm. Now, regarding an image is also a data set, no? It's a collection of pixels. It's a collection of pixels stored in form of a matrix. It's a collection of pixels stored in form of a matrix, right? So this is the example which I showed in my slide also, like same image. Is this the original image? And after you apply the wavelet transform to each pixels, you get this denoised one. So I will share this link for those who want to explore more about this. Okay, so just to what is the getaway message, like takeaway message from this is to understand wavelet can help in denoising data. Okay, and wavelet can be used in denoising image also. That's one of the key features of how to handle noisy data. Okay, how to handle noisy data. The two things, you can either denoise the image or denoise the data, or select the tiny part of it which represents the whole part of the data. Okay, so the next is like the pyramid algorithm. Okay, the pyramid algorithm Anyone knows about pyramid algorithm or something like that? So it's one of the DWT methods. It's the method of DWT we'll apply and see in action. Okay. So let us see this example over here. Like I will tell you. I mean, it's very simple. No need to get like too much worried about this algorithm. Very simple. Like suppose you have this data set, very tiny data set like 4, 6. It's an array like 4, 6, 10, 12, 14, 8, 6, 2. Right? All these are your data sets here. What you do is you create a level 0. You create a level 0 and each of them represents that data. Like you can create like this. Okay. So can you see those numbers here? So note that 4 is there, 4 is there, 6, 10, 12, 14, 8, 6, 2. Fine. That's the 0th level. Okay, that's the 0th level. Now, when you go to the next level of iteration, you do two operations. You do two operations. What operations you do? One is addition, one is subtraction. Okay. Okay. So D1 is like the subtraction one. So what you do is you take this element 4, take this element 6. Let me zoom it. Okay. Take 4 minus 6 and divide by 2. What you get? -1. So that is shown here. That is the first level obtained with difference. That is the first level obtained with difference. Okay. Next, what you do is now the role of these two element has finished. The role of these two element has finished. Now concentrate on the next two elements. Okay. What are the next two elements? 10 and 12. Now same thing. 10 minus 12 divided by 2. What is it? Again, you got this, right? Fine. Fine. So next, let us go to the next elements here. So what you have? 14 and 8. So what you will do? 14 minus 8 divided by 2. What you get? 3. So that is there here. Okay. Fine. So same thing you can do for here also, 6 and 2. Okay. So what you get? 6 minus 2 divided by 2. So what you get? So this is from the difference. This you got from difference, taking I mean neighbor differences, adjacent differences of variables. Okay. Now we will take the sum. Now we will take the sum. Okay. So that those are represented by the orange nodes. Okay, orange nodes. So let us write in orange only. So now instead of this, now you do 4 plus 6 divided by 2. What is it? 5. Can you see that here? Yes. So now let us do 10 plus 12 divided by 2. What is it? So that you see here. Okay. That you see here. Right. Same thing. 14 plus 8 divided by 2. Yeah. Again, what's the remaining? 6 plus 2 divided by 2. Yes. So this you created the new level. That is the level 1. Is it okay? Intuitive. Hmm? So in each level, when you go from the 0th level to the level 1, you do two operations. One is addition, take divide by 2, and take the subtraction divide by 2. Okay. Wherever, but we will focus more on the addition part. The difference tells us like how one data differs from the other one. Okay. But we are more focused on the addition part. Now what you see, that is my question. What you observe from this? Okay. How many elements were there in level 0? Can you tell? How many levels, how many values are there in level 0? Are you sure? 1, 2, 3, 4, 5, 6, 7, 8. 8. 8 elements are there. Fine. Any questions? 8 elements are there, right? Now, when you went to level 1, how many elements are there? 4. Now, when you go to level 2, how many elements will be there? If you go to level 3, how many elements will be there? 1. Yes, we are interested in that one element. Because all the data, like you are taking all the data values from level 0 and you are applying an operation and landing to the highest level point which represents a value, and that is representing a value from which matters to all the data values. Okay, that's like a representative value of all the data values. So instead of taking 10 or 8 values, Instead of taking 8 values, you will show only one value, and that is a representative value. Okay, so that's how this algorithm is a small example how to I mean compress your data. Okay, so I'll tell you in more details. Now you can do the same thing, right? What you can do, 5 minus 11 divided by 2, what you get? Minus 3. That is the second one. Same, 11 minus 4 divided by 2, 3.5. Yes, this is the same. Now can you add them up and divide by 2? 8. 11 plus 4 divided by 2, 7.5. So you got a new level, level 2, right? Now you see that from 4 values in orange, you went to 2 values in green. So your data set has decreased by 2. Okay. Now what is your new level? Level 3. 8 minus 7.5 divided by 2. 0.25, right? And what is the summation? 8 plus 7.5 divided by 2. So that is the highest level. That is the level 3. And you see this is a structure representing this scenario, right? So therefore it is known as a pyramid algorithm. Okay, because you go from bottom to top. You go from bottom to top, and every time you go, you are reducing your values, the number of data values, right, by 2. Okay, so this is the idea. But you can see that the bottom picture here, this is known as the A3 point, and this is known as the D3 point, right? This is the D3 point. The idea is A3, that is 7.75, it represents the overall average of the signal. Okay, overall average of your data set at level 0. Okay, 7.75 is a representative of the overall signal at level 0. Okay, so that's how PCA is also working. I mean, you have lot of features, you select the most important features which represent the data. Okay, so same thing here, you have lot of features. Now you should ask me how I can call 7.75 as the representative data set. Yeah. So why 7.75 is known as the representative data set? That means you understand how we constructed 7.75. We took all the data points and we took the sum of them and divided by 2, and again we went on to the top and we got the 7.75. Now you can start from 7.75 and go back to reproducing the original data set. Are you understanding what I'm trying to tell? You can start from 7.75 again and go back to reproduce the original dataset. Of course, there are some errors. You might not be able to reproduce the original dataset exactly, but there will be some errors, but that's a kind of a representation, nearby representations. Okay, so therefore 7.75 is known as the representative dataset or average baseline compared to the whole data you have. Understood, right? Now you went to the top. Now I am saying that why this is representative, because you can take this data point and apply similar operations and go back to the original data point again or original data set again. That is the idea. You can do that. You can do that. So that's the algorithm about. So therefore you can see that why this guy is the representative data set, and hence instead of these 8 values you can suffice with just one value. Instead of 8 values, you can suffice yourself with just one value. Okay, that's the idea. So this is can play a huge role in data compression kind of things, right? So we divided by 2. We divided by 2, and therefore this method is known as HAR, a discrete wavelet transform and this pyramid algorithm. But you can divide by root 2. Okay, I mean you can do this. See the level 0 over here. What we did, 10 plus 12 divided by 2, right? And we got 11 over here, no? Agree? Instead of that, what you can do? You can take a square root of 2 also. You can take a square root of 2, and that represents a different wavelet approach, not the HAR wavelet. So if in exam comes like perform a HAR wavelet analysis on this data set, then you have to divide by 2, not by root 2. Okay, that's the idea. So you can see together they give a 2-number compressed representation of 8 numbers. Okay, and this is useful for compression. That is, the signal can be reconstructed with far fewer values. You can again reconstruct the original signal with that small value, with the tiny value. Okay, but not exactly. I mean, you won't get 4, 6, 10, 12, 14, 8, 6, 2. You will get something different. Maybe 4 will be 3.1, okay, but it is closer to 4. You understood, right? It will be closer to 4. Maybe when you are reconstructing this from this value, when you reconstructed the original data set as an attempt, you might get some values like this. Like maybe 4 can be like 3.1, 6 maybe you will get 7.5, 10 might be you get 11, okay, 12 you can get say 10.2, okay, 14 maybe 10.3, like that. Are you able to understand what I'm trying to convince you, right, about? So this data set will be almost the same as the original data set, but not exactly, okay? So therefore, what you understood from this, that one value is a representative value. Why? Because you can reconstruct almost the same data set using the similar operations. This is the basic idea of why I am teaching you the discrete wavelet transform about, okay? How it can aid in data compression and things. It's fine, right? So that's the plan here. How much time we have? Oh, still we have time. Okay, 5 minutes break. 5 minutes.